Hi everyone, this is the Con Warrior. Right, in this video I wanted to show basically coil profiling, specifically generator coil profiling. What is it, first of all? It is a method for giving you an idea of what your generator coils are capable of doing. How most people, when they calculate generator coil output, just hook up, say, a bulb, measure the voltage across the bulb, measure the current going into the bulb, and calculate the wattage of the coil based on that. However, after discussions with Vespa, with regards to how we should be testing the coils, a bulb, yes, it's a very good indication. However, most generator coils are capable of much more than just driving one particular load. So, in this video, I want to show how to map out your coil. So, what have we got? For testing purposes, we have the SSRG. We have a refitted coil underneath there, drive coil that is. It's had a few modifications done by me to make it a bit more, give it a bit more oomph behind it. Now, obviously, I've got a Vestgen generator coil underneath there, a genuine one for this purpose. We're testing to see what the differences are between using magnets to generate the power and using electromagnetic coil. But that aside, we can still continue. So on this side, we have the wires going into the drive coil, and outside, on this side rather, we have a loom coming out for testing purposes. Yes, it's a huge loom. Wired it up to this block. Now for this test, we just wired all the sections in series, basically to make life a little bit easier. So, here in the vise, we have a bunch of resistors. They've been super glued down to a heatsink because we will be using them to dissipate more power than they're actually capable of dissipating themselves. So I've just super glued them to a heatsink and then encased them in hot melt glue. So basically they don't come off and the wires don't snap and there's no contamination, etc., etc. So, unfortunately, right before this test, when I was already starting to get the figures, unfortunately, one of the multimeters died on me and refused to measure voltages. Specifically, it's this one. So, at the moment, I've stuck it back on measuring amps. So, as you can see, the display on it is, yeah, it's half gone. It's near its end of its life. So, oh well. So we'll have to make do without it. It's not ideal, but I'm going to talk you through it anyway. I might have to do another video. So, the only decent multimeter I've got is this one. On AC amps, AC volts, we're measuring 0.879 at this time, which again is different from the figures that I've got. Right, how do you do the testing? Well, as I said, here we have a load of resistors. We have one that's 2 ohms, we have 5 ohms, what turns out to be 10.1 ohms, 19.6 ohms, 49 ohms, 98.2 ohms, 216 ohms, 325.1 ohms, 459 ohms, and 978.9 ohms. Right, they seem odd values, but that's what they tested out to. So we've stuck the multimeter in resistance measurement, and we've measured each set of resistors. Now, one thing to remember before you do that is to get the bias of the multimeter. In order to do that, you simply, we'll do it now for you, take the multimeter, resistance mode, and then join the clips together. And as you can see, it gives you the bias of the multimeter. Right. Luckily enough, it's reading pretty much zip. Obviously, we can see a 0.1 coming up occasionally there, so we'll take the worst measurement and we put that in as DMM bias. So, I will try and do this with one hand. Don't you just hate that? Ah, just bugger. Whoops, daisy. Huh. Mental note: don't connect multimeter up to a gen coil, but it's still in resistance mode. Generally tend not to like it. Just excuse me a second. Connecting these things up is a pain. I need a better way of doing that, but I'll sort that out later. Right, so we currently have the 2 ohm resistor set on there. Now normally, because one of my multimeters has died, normally we'd have the voltage and the current being measured at the same time. So, for the purpose of this test, we will assume we have a virtual multimeter, and it will display the results of Ohm's law. This one is measuring AC voltage. The virtual meter is measuring AC current. Now, we go through all the resistors in here, get the voltage reading, and then with the use of Microsoft Excel, we put all the values in. As you can see, we have DMM bias in there. Now, this column here, right, is the actual reading from multimeter. That column there is just a calculation of the multimeter's reading take the multimeter bias. Right, so they're all the same, but what can I say? And it shows the resistance there. Voltage AC here, that comes from the multimeter itself. Just literally type it in. Now we've got originally going to put in AC current in there as well, but as I said, I've lost a multimeter, so I can't do that. Simple formula for calculating the voltage based on current. So again, Ohm's law to calculate a voltage. Right. Calculated amps, again, Ohm's law based on resistance and voltage. AC power, now this one is just the wattage calculation from AC voltage and AC current. But we don't have AC current in, so I've added an extra column for calculated power based on calculated amps. Yes, straight away everyone's going to go, you can't do that. But as I said, this is just for demonstration purposes. Go away, spider. Oh, little spid. Yes, shoo. Right. So, what we've done is we've gone down the resistors, measured the voltage, and it gives us our calculated power. For the purposes of this video, as I keep saying, we're going to assume that the calculated amps is the recorded amps from a multimeter. Right? Normally you would need to do them both at the same time. Please note I said at the same time. Do not try to use one multimeter to measure the voltage and then flip it around to measure current, because the addition of the multimeter in to measure the current changes the overall resistance. So you need to do them both at the same time. Technically, you should measure the resistance of the multimeter measuring current as well, and then put that in for the DMM bias as well. Well, either the DMM bias or the DMM resistance, whichever you want to do. They're both more or less the same. So, as you can see here, calculated amps, yes, we know. It drops down. Let's see if we can get this to focus reasonably well. Definitely need a new camera. I had to move my laptop, it's about a metre away from the coil. Make sure it doesn't get wiped by the EM field. Right, so here's the calculated power, which we're going to assume is the actual power. Right, it's not far off because I've done checks. So, in wattage, at 2 ohms resistance, we get 0.388 watts on this particular setup. Right, now, this has a reasonably linear progression coming down. Right, so as the resistance goes up, right, the power output comes down. Now, as you can see, according to the calculations, right, the most power available, right, is at 2 ohms. Now, not all coils will be like that. One of the good things about logging them down like this is that you can then put them in a graph, which is absolutely pointless for me to do here because these values are actually linear. Roughly linear anyway. So all it will do is show a straight line for this coil. However, those running rotors, basically most coils that are out and about have lens. Yes, it's a swear word, I know, but what can I say? Now, whether it's lens assisted or lens lagging is neither here nor there. The rotor speed, once you load down the coil, will change, right? Which is bad. As I keep telling people, right, change only one thing at a time. Go away. Right? So, in this case, the only thing that we want to change, right, is the resistance that we're using to dump the power. So, one of the advantages of running the SSRG is that regardless of how I load that coil down, the SSRG runs at the same frequency, same duty cycle, same input voltage. That spider is starting to annoy me. I don't know what the hell it's doing, but it just seems to keep dropping back down again and climbing back up. Very well. Now, on a rotor, unless you have a huge motor driving it that will overpower any lens produced, then the rotor will change speed, which is bad. Now, on a pulse motor type setup, if the speed starts changing, then the tuning needs to be redone because you're adding drag to it and yada yada yada, and you get all sorts of issues. Right, so even though I know the arguments against having huge motors to turn a wheel for doing testing, right, unfortunately, I definitely agree with Vespa, 100%, in that you need to overcome, you basically need to make sure that the rotor RPM is the exact same regardless of the test, from one test to another to another to another, within a reasonable margin of error, say 0.1%, something like that, maybe 0.5%. I don't think a couple of RPM here or there will cause any issues. So the more stable you can make the rotor, the better. So, first rule of testing, keep everything the same. And that's what we're doing. Change one thing at a time, and we're away. So, we change the resistance, we get the voltage AC. As I keep saying, calculated amps we're assuming is actual amps, even though it's not. I'm going to have to find out some way of measuring the AC voltage to do a proper test on this coil and tune it properly. So I'll just chuck this video together just to make people aware of how we are testing. How you want to test is up to you. I'm just giving you what can I say, the way that we're doing it and the justification for the way that we're doing it. So there you go. Those that do manage to do this, what you will quite often find with iron or steel core generators is that you won't get a linear graph. If you do power crap, mine's gone blank. Yeah, if you do output power versus in our case say resistance, you could also do output power versus RPM if you're testing that way. But anyway, you won't find a straight line graph like we have it. What you'll find is the graph will curve and do that. So it'll start off quite steep, then it'll flatten out and be very flat towards the end. Right? This is because the iron core causes issues. Right? So what you'll actually find is the power that you actually have, right, it's going to have a peak power at a different point. Right? So you can then use that peak power and tune the coil for the peak power. Hopefully that made sense. So if, for example, you wanted a coil to charge a 12-volt battery and you wanted it to kick out 12 volts, using this, right, you can then work out roughly 12 volts on the graph, come across, and that's how much amps you're going to get, because all your data points will create a line. So that should help you. As always, my home is on Teep. Feel free to drop in, sign up with a user, and say hi or ask any questions you want. Hopefully that made sense. I think I explained it properly. So, as always, any questions, feel free to email me. Talk to you later.